morning, everyone. Thank you for joining us on Sunday morning. I know we've done some things differently this year, but I think it's been worth the getting used to, because we've had some terrific panels. Thanks to the co-chairs of the meeting and our board, we decided to add additional content way beyond the science. And we're ending with a real special event today. We have a magnificent panel of speakers. Each in their own right could be keynote speakers of our event, and I encourage you to look up their backgrounds. I'm going to be quick in introducing them, and I think you'll enjoy what they have to say. It seems like this year's meeting had the AI theme, as many meetings have lately, and particularly in our space. We started with Eric Topol on Wednesday, who started a conversation on AI and aging and healthcare, and we're ending with the same. So we hope you enjoy this presentation, and thank you for attending the BMES 2025 Congress, and we hope to see you all in Orlando next year. So the conversation's on AI and medicine and pedagogy, and the panel is comprised of Dr. Brian Anderson, the CEO of the Coalition for Health AI, Dr. Michael King, the professor and CPRIT scholar at Rice University, who most of you probably know. He's become a bit of a social media sensation with his writings on AI and use of AI in the classroom. And Panta Kodami, the worldwide head of life sciences and precision medicine at Amazon Web Services. And due to the government shutdown, we had another speaker from NIH, Dr. Rui Desa, who obviously is unable to make it today. It is now my pleasure to introduce our moderator, another person who I think you all should look up. Dr. Daniel Kraft is the founder and chair of NextMed Health. He's a physician, scientist, inventor, entrepreneur. He's done it all. He's Harvard trained. And I leave you in very good hands. That's all the introduction, short and quick. Thank you so much.
All right, fantastic to be with you all. I have an amazing panel. I was asked to kind of give an opening talk to kind of set the stage, and it's always great to be in sunny San Diego. And it's an incredible time, and as we heard, we have a government shutdown. We have other wins and challenges in healthcare. But I love this quote: "The pessimist complains about the wind, the optimist expects it to change, and the leader adjusts the sail." And you guys are all leaders in biomedical engineering and beyond, and we have these new technologies that are back, AI and other technologies that can help us push the entire field of health medicine forward. And of course, I didn't make those images myself. I'm all cheating like we are with GPT and engines. And of course now you can make almost anything from text to video, and including still some mistakes that happen in these platforms. So harder and harder to tell what's real, but see if you can see the challenges. Of course, I did this on the airplane last night. You can do some fun things, almost basically for free. You can bring the gorilla when you want to, too. So it's a pretty interesting time. And of course, it's getting harder to distinguish what's real, but it just gives us ways to have some inspiration. Let's play the video.
The future of biomedical engineering is coming faster than you think. Let's create it together.
Right, and of course, creating that is now being done more and more with AI. And of course, GPT only launched, just under 3 years ago. It's the fastest moving technology on the planet. And for physicians like me, it's already doing a much better job, at least passing the medical boards. And now patients aren't going to Dr. Google, they're going to Dr. GPT, often finding problems that specialists missed. We're being defeated in terms of making medical diagnosis. And bottom line, I think the flavor of you're getting this in the meeting over the last few days as well, these technologies are moving quickly, sometimes faster than regulatory, policy, education, ethics can keep up with. And so the future's coming a bit faster than we think, and particularly for many of you who are students, you're going to be creating that future, and it's only accelerating. I don't know if this is actually real, but an example of acceleration, China's doctorless health, building doctorless machines. And there's a great piece out last month: if AI can diagnose patients, what are doctors for? What are biomedical engineers for? What are our roles going to be in this convergence of accelerating technologies? And of course, I'm not a bioengineer myself, but I like to play with them. And BioE, all that's at this sort of synergy where AI, systems biology, new forms of data are coming together. I do have a bit of a bio background. When I was a fellow at Stanford on faculty, I helped them get the bioengineering program together. I was part of the first year of Stanford's biodesign program, where it's all about finding problems and solving them, often in the medical device space, but broadening it out further. My pain point when I was doing my bone marrow transplant fellowship was harvesting bone marrow. It's a very old mechanical suction approach. It takes about an hour on 100 punctures. So my little innovation was something called the marrow miner. I guess it counts as a biomedical device where we could, instead of doing hundreds of punctures, go in there with a flexible shaft, and now we can do an entire harvest in about 5 minutes under local anesthesia, and it sort of looks like this in real patients. So kind of a convergence of my non-engineering mind with collaborating with engineers to make a better way to harvest bone marrow. And now we've been doing a study on the Gates Foundation to look at delivering genes into the marrow cavity, not taking bone marrow out, to do in vivo gene therapy. So we maybe can democratize that. This is in some animal work at UW. So back to AI for a second, the theme of today. Here's a fun framing element. Here's a book from 2021, which I read, A Brief History of AI, where it is, where we are, where we're going, and all those topics at the bottom were nowhere near being solved. And of course, GPT came out, and most of them are close to being solved, and you could argue when we're going to reach AGI. And it's still early days. Just as a reminder, it's still AI is making mistakes, has biases, misinformations, hallucinations, and there's also some sort of cognitive downsides. There's a famous quote from Sam Altman, the CEO of OpenAI, that GPT is like an e-bike for your mind, which is great, but what if your kids never learn how to ride a regular bike or never develop their biking muscles? Or you're a BioE student, you never design a medical device or solution without the help of AI? Or the kind of de-skilling that can happen from MIT Media Lab. Your brain on GPT writing essays gets less skilled if you're spending too much time using the GPT engine. Or in the medical space, clinicians using AI to help their colonoscopies started to reduce their skill set. So there's some challenges and opportunities as we learn to collaborate with these technologies moving forward. But like many of you, I'm an optimist. I don't think about sort of just Gen AI. I think more about generative health, this idea that we're entering this multimodal era that's going to be more agentic built. So these agents will know our age, our culture, our language, our personality type, our health goals, our digitome, all that data coming together. And we'll give it this pretty exciting era of agentic health and start to make sense of our biomedical data, right? Google recently published some new elements about a personal health agent, leveraging wearable data and other information to glean the true insights, not just the raw data and your sleep score. So big picture, I think the future of biomedical engineering, health and medicine broadly is going to be a little more intelligent, more digitally enabled, a little more precise, personalized, preventative, and big picture can be made more accessible and more democratized around the planet. And made more impactful and at lower cost. And can take us where we are today, really in an era of intermittent reactive sick care based on one-size-fits-all therapies in many cases, data that's only collected in the four walls of a clinic or hospital, and move us to what's next, an idea of true healthcare that's proactive, preventative, anytime, anywhere, hybrid with physical and virtual, leveraging AI with biomedical engineering and new knowledge at the interface, and aligned with our incentives and workflows. Now, we're in 2025, which used to feel a bit, was going to be the future. Now we're in the future. But when I go back to MGH, where I trained in internal medicine and pediatrics in the late 90s, it hasn't changed too much. I still get a little PTSD when I go back and visit the White 9 ward, where I think Brian spent some time as well. Same nurses, sometimes the same patients. The alarm's beeping, give me a little PTSD. But the only difference is the intern doesn't handwrite the medical record now. They type it and push around a cart. And they're still using the cutting-edge medical communication tool to get their pharmacy prescriptions to CVS, the fax machine. Billions of fax machines, and lots of paper is still pushed. When I had a cardiac study done at Stanford last year, how did I get my results? On a DVD. I don't even own a DVD player anymore. So we're stuck in sometimes the old architecture of the past. I would argue, billions of faxes, spending more of that on cancer. And in the biomedical space, many ICUs and clinical realms are still kludgy and wired up in old modalities. So it's our opportunity to sort of reimagine that and bring health and biomedicine and BioE into the fourth industrial age where many other technologies and fields have reached. And of course, it's not just about AI. It's a lot of other technologies we'll talk about that are the super convergence of moving health and biomedicine and biomedical engineering forward, getting cheaper, faster, smaller, better. And that's when you mash them up, that's where you can do some interesting things. So all these technology sets didn't exist when I was a Stanford medical student. We didn't have LLMs, low-cost gene sequencing, robotic surgery, wearables, CRISPR, virtual reality. All these new tools, especially those of you earlier in your career, are going to leverage to address all the grand challenges we have across the planet in health and medicine, from rising costs, an aging population, access to care, whether it's Obamacare or Trump care, which is really no care, to making sense of all the data that's siloed and fragmented in fax machines and paper records, or to the regulatory side, the F word, who has the challenge of taking some of these exponential technologies and helping them move from invention to impact. So my challenge for you today and for our conversation is to not just think of where we are in 2025, but where we're going to be in the next 5, 10 years is going to be quite incredible. And of course, it's not just about the medical side. We're in this era. I come from Silicon Valley, where a lot of folks are interested in longevity. That's I don't know if you really want to live forever, but I think most people want to have health span. We want to extend our health span and shrink our sick spans. And maybe the GLP-1s are a new form of true longevity-related meds. But we're entering this time where we're going to start to potentially engineer our aging, and that has lots of broad implications for society. We're on the cusp of making that happen. Still a lot of snake oil out there, a lot of charlatans, but it's going to blend more and more with the stem cell and regenerative medicine world. So what's next at this convergence for biomedical engineering? I wrote the opening article for Nat Geo a couple years ago, The Future of Medicine, and it wasn't really about 12 innovations. Again, it's about how you put these innovations together, and not even about just the innovations, which many of you have been building and researching and developing, but they're not sufficient, right? Because you might have the best new stent or device or biomedical innovation, but unless it aligns with the workflows and incentives, we're in trouble. Because at least in the United States, we don't practice evidence-based medicine, we practice reimbursement-based medicine. That doesn't always align with the best solutions. We need to start moving the incentives to prevention and health. And also, at the cusp and the convergence of BioE is where care can happen, from hospital to home to phone to on to inside our bodies. And the incentives are pushing us in that direction. So I've played an accidental role as a bit of a futurist looking at this convergence for the last 15 years or so. Chair of medicine for something called Singularity University, thematically around exponentials. Built a program called Exponential Medicine on the theme of all these things coming together. Now it's called NextMed Health. We run it every year just down the road at the Hotel Del Coronado. And we had this spring Eric Topol and Dean Kamen and Larry Brilliant and folks doing everything from drones to psychedelics to chatbots, of course, to AI as well. And the theme there, just the reminder, is to get yourself out of your silos. When you bring folks together, you can change mindsets at the interfaces of different fields, which I think bioengineering is a really great example of. I love this quote from Tony Young, head of NHS Innovation. The difficulty lies not in the new ideas, but escaping from the old ones. So you guys have a lot of new ideas, but sometimes your colleagues or health systems, from big pharma to the payers, do not yet. So come join us probably in San Francisco this next fall. So let's look at a few things on the exponential and how AI is playing with that and biomedical engineering. Of course, the price of sequencing, something done down the street at Illumina, has dropped from $10,000 roughly a decade ago to about $80 today, on the way to a $10 genome. And that means all of us will be sequenced, and our patients and our populations, for less than the price of a cup of coffee pretty soon. And that means we can start to really do precision pharmacogenomics at base and start to pick the right drugs and devices and solutions that really match the individual based on their genomics and other data. According to your genome, you're genetically predisposed to obsessive over your genome. So lots of information can be leaned in there. And of course, information is not enough. It needs to flow back to the clinic. The folks at Genomics England are connecting the dots between big data sets and insights back to the nutritionists, pharmacists, genetic counselors as well. And I'm going fast, I'm sorry. There'll be a QR code at the end to get all my slides, so don't try and keep up. And speaking of genomics and AI, many diseases, common diseases like type 2 diabetes, are really rare diseases. When you subset them up, like there's at least 3 distinct subtypes or more of type 2 diabetes that respond differently to prevention, diet, medications, and other interventions. Of course, we're not just reading DNA, we're in the era of writing DNA. Many of you are working with CRISPR, which is a relatively new technology, and it's moving so fast. One of my fellow Aspen fellows is an ICU doctor. He climbed Mount Kilimanjaro about a year ago. Not a big deal for him, but he brought with him Jimmy, who until about 6 years ago had sickle cell disease until he was cured by CRISPR-based therapy. So pretty incredible he can climb Mount Kilimanjaro as a former sickle cell patient. And of course, got to tell that story to Jennifer Doudna. And of course, we're starting to be able to CRISPRize and personalize and use AI to design new forms of personalized CRISPR-based therapies. And that's going to have huge implications across biomedical engineering. And of course, blending that with proactive therapies, right? The idea that one of my colleagues from MGH has now developed a platform where they're delivering genes to the liver to knock out the genes for hypocholesterolemia. So you never develop high cholesterol and the plaques that are associated with that. So an interesting time to leverage AI, drug discovery, designer mRNA vaccines and beyond, to think about health span and proactive therapy, even vaccines for cancers, neurologic disorders, and beyond. Now, of course, it's not just about engineering with the genome. We're now in the era of the low-cost proteome, the exposome, where there's microplastics or pollution, the metabolome you can measure from over-the-counter CGMs, the microbiome in our skin and our gut play a big role in that. Just measuring the proteome alone enables, it seems to, from a recent publication, to predict Parkinson's several or 8 years before symptoms arrive. Or now the immunome is being measured. So now we're overwhelmed with different omes. It needs to become multimodal, right? It's not any one omic, it's how you mash them together to make sense of that, sometimes synthesized in this idea of this sort of AI-enabled digital twin, where you can start to model what's gonna be best for prevention, diagnostics, and therapy. It might be the heart. It might be, in my field of oncology, precision oncology, using a digital twin of that exact patient and that tumor. And then, of course, potentially engineering precision health span, because a lot of these one-size-fits-all longevity regimens won't work either as well. So another cartoon, all done by AI. Good news, your digital twin is in excellent shape now if we can only get you two to sync up. So opportunity to blend the two together. And even to start to super enable us going forward, a whole other topic. So the world's moving quickly, it's moving exponentially. What used to fit on a Cray supercomputer now fits on your smartwatch or your smart ring. Quantum computing is going to be hugely impactful in the next decade, so watch that space. And basically, a lot of the analog devices of at least my past have all become digitized and democratized and demonetized and can come anywhere, anytime. And that has where BioE can go almost anywhere. Of course, a lot of that already today lives in our smartphones. Our smartphones are dissolving into our visuals and are still kludgy and a bit expensive Apple Vision Pros, and soon will be in our contact lenses and our augmented reality glasses. And that gives us the ability to bring these agents and new knowledge workers and collaborators into our space. Our brains don't know that these aren't real, but we respond to them as if they are. You can design your own avatar and agent in high resolution. I can type a note on the airplane as I did now, and my avatar can speak for me.
Well, hello there. This is Virtual Daniel. On behalf of avatars everywhere, it's wonderful to be in San Diego with BMES to explore the future of AI and biomedical engineering. Now, I'm going to rest my neural circuitry, so I'm handing it back to Real Daniel while I go to the beach. I'll see you back in the Metaverse.
See you virtually. Thank you. So it can augment you. It can augment your clinical teams to come into virtual spaces. It's, of course, now upskilling all of us so you can blend this data with spatial computing. I still have my antique, pretty cool engineering from my Google Glass, 10, 15, 13 years ago now. But now these start kludgy, but are becoming commoditized and commercialized, like the Meta AR glasses, which you can now buy. So that gives us new ways to glean information, whether you're a student, an engineer, a physician of any sort. Whether you're trying to plan for a surgery or now do a surgery, and now the surgeon to see through the patient's body and be guided step by step on a spinal fusion and do a much better job than the average surgeon, for example. So lots of this is starting to blend together and gives new insight when you can be multimodal. You can also take lessons from other fields. I'm a pilot. I served for 14 years in the Air National Guard as a flight surgeon. We use kind of augmented reality in a fighter cockpit. The heads-up display means you don't need to bury your head in the cockpit. You can see through this plane and know where the bad guy is, who's shooting at you. It can also give you audio clues. If you're about to hit a mountain and you're not paying attention, that'll wake you up. So how might we apply that to the biggest challenge in healthcare, which is often behavior change? So imagine you're trying to lose some weight and get healthier. You see your morning breakfast, now you have your AR glasses and you see some new information and you get a little bit of a nudge. So that's kind of our dystopian future. And when I learned to fly, Brown University Flying Club, $20 an hour for the airplane, round dials, paper maps, and a Cessna 150. My new plane is the same size, but it has a glass cockpit. It has situational awareness. It brings all the contextual information on a touchscreen GPS, traffic, weather, frequencies. You can fly just with the screen itself. And so that technology and that insight doesn't just need to be on the screen of a fighter pilot, but can come to all of us in the biomedical world to give us just-in-time synthesized insights. I was just in Israel a month ago. They're building smart hospitals to kind of bring that insight into air traffic control for hospital endeavors so they can know flows and not keep folks stuck in the emergency room. So again, connecting those dots in these sort of dashboards, many lessons from aviation. And back to sort of this augmented world, we can now see our future selves. Our digital twins can kind of show you a future self. You can see you of today if you're doing your P90X and workouts in Peloton, or you can see yourself tomorrow, you of tomorrow if you're eating Dunkin' Donuts every day, right? And that can give you incentive from being here and only having one donut, because I can see the future, right? Or if you have a friend or colleague who smokes, you can show them before smoking and after smoking. That's a powerful lever for change. Or what happens if you spend too much time on social media? I don't recommend that. And so bottom line, we can all become avatars and see our future selves. Now it's getting easier to sort of turn ourselves into digital beings. And then there's, of course, virtual reality, a big tool across health and biomedicine. Putting grandma on a roller coaster is a little cruel, but it's a tool for collaboration. I'm sure many of you are using it to design devices and to collaborate. It's a great collaborative and learning tool. It's taking kids and making them less scared to get a vaccine or see what's going to happen in the hospital. It can be used instead of opiates to get burn patients to get off of pain meds while they're having very painful procedures. So it's becoming a therapy almost as well, including in physical therapy, which overlaps with biomedical engineering. No one does their physical therapy very well, but now you can gamify it, make it fun and engaging. And of course, for education, for medical school, for example, I trained see one, do one, teach one. The future is going to see one and simulate it, often with collaborators, sometimes from around the world in real time. So big changes are coming there. And back to sort of the engineered clinical space, the black boxes for airplanes are coming to the operating room so you can measure almost every element and then give sort of real-time GPS and guidance to take the below average surgeon, and 50% of surgeons are below average, and upskill them with that sort of knowledge. And of course, robotics are entering that space. They're becoming more and more autonomous, and it's going to be an exciting time to see how we blend robotics and procedures going forward. And eventually, I think that takes us to this realm of, just like regular driving became partial assist to full assist, and now you see Waymos and self-driving cars. That's going to upskill many elements of the clinical endeavor going forward, but still having humans in the loop. What about diagnostics and AI? We need to blend those two together to find diseases earlier. We're now engineering scales that don't just do weight, they can do your shape, measure your muscle mass, your fat mass, and other contextual information that could be part of your weekly or annual physical exam, and give you context about change. You don't even need to bring a device to measure vitals. Of course, you all know that cameras can now pick up vital signs pretty seamlessly, and now it's going to add blood pressure and probably blood sugar and beyond. So lots of insights can be democratized for gleaning biomedical information. We're in the era of the medical selfie. You can take a picture of a wound and use AI to predict what might be best and how it's going to progress. Or I'm on the board of this Israeli company where now instead of bringing the urine to the lab, you just dip your urine at home, and now with an FDA-cleared platform, you can dip it and determine does the patient have a UTI, preeclampsia, early kidney disease, and be much more proactive, very easy and low cost, as an example of a lab on your phone. And back to the phone, the microphone is a diagnostic platform. It can pick up using AI where the sound of your voice means you're having an early neurologic issue or a mental health issue, or is that cough cold, croup, or COVID, right? And now some recent data published, we know a lot of undiagnosed diseases out there. The sound of your voice on your microphone on your phone can pick up high blood sugar and find folks who are pre-diabetic or diabetic or even hypertension. So lots of new ways to synthesize insights and do earlier diagnostics proactively. And where that takes us is an opportunity to sort of measure our behaviors as well that are the biggest drivers of our health costs and mortality and morbidity. It started roughly 16 years ago. The first Fitbit was only 2009. Now these wearable and otherable devices, and some of you are making them and building them, can measure almost every element of physiology and behavior, right? They're starting as consumer quantified self devices, but moving to medical. And they're getting interesting right now. For example, of course, Apple Watch is becoming an integrated device, and they announced last month that they're starting to measure blood pressure. And there's actually devices that are FDA cleared that can do real-time blood pressure, and some that are on their way to doing real-time blood sugar. So imagine when each of us and our patients is streaming our real-time blood sugar and blood pressure and other data 24/7. How do we make sense of that? Or the idea of ingestibles, biomedical engineering coming together in the PillBot. I got to try this, swallowing this very large pill, amazing engineering with NASA engineers. And here's what it looks like when I swallow this pill.
Breakfast of champions.
It's basically replacing an upper GI with a $500 technology that you can do anywhere. So I'm swallowing this big pill, goes down my esophagus, and now I'm steering it with a game controller while talking to the head of GI at Mayo Clinic.
Nice. Live from New York or live from my stomach, we have the PillBot from Informatics. Let's have a little look at my inside, shall we?
So I drive that. I won't bore you with my insides, but that's pretty amazing engineering coming together. There's now patchables that you can drive with body movement, earables. The ear is a great space for picking up data and giving cognitive support. Sweatables if you're running a marathon or have heart disease. Insidables is at your convergence of that. The challenge is these create lots and lots of data. Even electroceuticals, which are measuring and using electricity as therapy. The trick is you don't want a wearable for every sort of vital sign. We're starting to see this convergence, right? There's patches like this that can basically be an intensive care unit level of data on a disposable or rechargeable patch. That means the patient can be admitted to home or discharged faster. And it's not just the data, it needs to have the operating systems to make sense of that. And then this is coming to the consumer. How many of you are wearing a wearable right now? Just curious. About a third of you or so. And of course, they're getting better and cheaper. Have any of you ever used a wearable with your clinician? Nobody, right? Well, that's getting interesting because these are coming from consumer to medical, right? They're able to track your sleep, and many of you might need sleep after this week. But they can also pick up pregnancy 5 days before home pregnancy test, or they can predict who has COVID a day before they have PCR positivity, or measure a response to a vaccine. So they can be great public health measures. So leveraging very low-cost devices in the population can be powerful. Or the future of the physical exam will be all measured continuously. This is work from Benjamin Smar at UCSD looking at high-risk pregnancies. And you can measure continuous biomarkers from a ring or a smartwatch or a Fitbit and tell which pregnancy is getting in trouble days or weeks before they might have a major problem or complication. And it doesn't need to be fancy data with fancy devices. The Fitbit can measure your mobility, right? You send a patient home from a total hip replacement with a new medical implant. Are they walking more each day and doing better, or walking less? And maybe there's a problem you can be proactive about. And that brings us to this idea of mobility as a vital sign, something that's not really in our medical charts, but now you can start to measure that with AI and a camera. Here's me getting measured for my mobility and getting a mobility score. Imagine that, which is a lot of biomedical engineering based in there, can give me some insights. And if I need them, I can wear an exoskeleton. I got to try these exo boots, which is great. I also, when I was in Europe last year, got to try a 3D printed exoskeleton for paraplegics. And with AI, it learned me and walked me around. It was quite amazing. But that's a blend of Bio-E and AI to help disability. And of course, those are getting more consumerized. So you might be 90 and you want to climb Mount Kilimanjaro. You put on an exoskeleton and get to climb the mountain. Or many of you know my friend, my hero, Dean Kamen, biomedical engineer extraordinaire. He built not the Segway, but he first built the iBot to enable folks with disability to get around. And that often starts with medical problems that can consumerized in new ways. And really amazing magical technology from Dean. And then my favorite wearable in Bio-E technology, of course, is the jet suit. It's being used to rescue folks in mountains when the helicopters can't get there. And I got a chance to fly that a couple years ago. Most of the time, I did not look like James Bond. Most of the time, I look like this. But the ultimate wearable and biomedical engineering coming together. A lot of human factors in there. Okay. So back to engineering diagnostics, right? It means these tools can now fit in our pockets and upskill a community health worker, or each of us. There's now stethoscopes with AI that listen to your heart sound and do an EKG and are much better than me and most cardiologists in diagnosing a murmur. Or low-cost ultrasound devices that are able to be democratized anywhere in the world. So from rural California to rural Rwanda, we can apply diagnostics. And AI can now enable anybody to do an ultrasound, even on themselves, and get a FDA-cleared, in some cases, diagnosis. Or home testing for COVID. I chaired the XPRIZE Pandemic Alliance. We ran an XPRIZE for frequent, fast, cheap, and easy COVID testing, which we didn't have in 2020. And 700 teams from 70 countries competed. We had amazing winners developing amazing new forms of home diagnostics, not just for COVID, but for non-infectious diseases as well. So lots of new home testing at the blending of engineering and diagnostics is going to be a big game changer and will democratize care. Lots of new ways you guys know about looking back at the eyeball and AI. Pathology is becoming digitized. A colleague at Stanford now can put a sensor, OCT, on the skin and basically do a virtual biopsy of skin, so you don't need to have the actual biopsy. So I think we're going to see this sort of convergence of not radiology and pathology, but diagnostology coming forward as an example where AI blends the two together. And of course, AI is not just on your screen, it's becoming physicalized. The idea of human-embodied robots is getting quite dystopian, but now they can become more autonomous. Maybe it'll be your virtual pharmacist, maybe it'll do virtual care. They also can be social, right? A lot of social isolations out there. We want them to be nice and user-friendly. I had a chance to interact with a few of these robots recently, and it's a bit dystopian for a bit, but they become more normal. Or you can maybe train your AI-powered dog to have a ChatGPT engine and help older folks be safe at home. So that's coming fast, and that's the convergence of AI and biomedical engineering as well. Let me close in the last 2 minutes just to remind you of that. It's not about human versus machine. It's how do we collaborate, right? AI is not going to replace your doctor or your biomedical engineer or your pharmacist, but those using AI will replace those who don't. And you don't need to wait for that future. Digital health is often at that sort of interface of AI, sensors, biomedical engineering. We're starting to prescribe apps and not just devices and not just drugs. Often the drugs and devices come with apps on top of them. You might prescribe a video game that's better than Ritalin in treating ADHD. And where this takes us is this era of quantified self. Many of us are tracking our steps and our sleep and other data to quantified health, where we're going to be able to measure data continuously again, diagnose diseases earlier, and then have smarter feedback loops for therapy and kind of drive an era of what I like to call predictalytics, or a bit of a check engine light for the body for each of us and our patients, leveraging multiple sensors to give us early warning to the point where, a Stanford colleague developed ways for your smartwatch to pick up COVID, or now even your Apple Watch with the Vitals app, which some of you may not even know you have, can look at your baseline and see how it changes when you might have been exposed to a virus or have something else going on. So this is starting to come to reality. And I would expect by 2035, we'll be in this Minority Report world where you're going to get a nudge when you have information before you know it. I'd ask where it hurts, but your wearables have already booked you an MRI. So again, challenges and opportunities as these things come together. And this world's already pretty broad. There's thousands of these solutions out there. I couldn't track them all, so I built a platform recently called digital.health. That's the website. If you all want to go to digital.health, you can look through lots of what are actually biomedical engineering solutions. For example, the EKG in your pocket, right? You can learn about the product, its evidence-based. You might prescribe it to a patient or put it in your own digital formulary. You might be interested in AI-based tools that leverage UIs for medication management and diet nutrition for reversing diabetes, for example. So whole new sets of tools are available out there. You don't need to wait for the future. And this future, again, coming faster than you think, is creating lots of data from all your devices and solutions. No clinician wants more data, right? It's not about more data, it's about more insight. And a lot of the data is still very siloed and hard to put together. So the challenge and opportunity for all of us is not to go from exponential data sets, but to turn that into actual information and insights. It's not just published in New England Journal, but comes to the bedside and the website within minutes, not 17 years. So that's this implementation science field that's moving forward. And ideally, we can catalyze that by starting to crowdsource data, just like we crowdsource our driving information when we drive in Google Maps or Waze. Imagine, as you all cross-collaborate, sharing data and insights, maybe from your own health journeys, to help those with others and build solutions faster. And at this super convergence of engineering, if any of you have been in San Francisco and drove in, or LA and been on a Waymo, think of health and biomedicine was much more like self-driving health. Just like a Waymo comes on demand, it knows who you are, it has transparent pricing, it adapts to the weather and the traffic, it's crowdsourcing its journeys. That could be the future of health and medicine going forward. I'm going to skip the future of care, just to make the point that you can start talking to agents going forward. I can upload my data and now talk to a prototype of an agent, knows all my data continuously, we can access them anywhere. And that begs the question, I think we'll talk about at the panel, how do we train the biomedical engineers and physicians of the future into this new AI and digitally enabled age? I'll end with a little bit of therapy and how this might all come together. There's lots of new technologies for drug delivery, as you're well aware, but a lot of folks are on polypharmacy. What do we take the biomedical engineering world of 3D printing, which is applied to braces and implants and stents, and might think about the challenges of polypharmacy and precision medicine. So I've been working on a solution to take the right data, pick the right combination of medications for a chronic disease patient, and instead of taking a pile of pills, we're able to sort of print one pill. And in telemedicine, the idea is, the ability is our prototype printer, is to sort little microspanules and build your personalized polypill that would adapt to you. Starts with a big printer at your corner pharmacy or PBM, but eventually can come to your kitchen counter and print modified print. So that's kind of a combination of AI, big data, machine learning to hopefully bring us a personalized future of therapy, whether it's your longevity capsule or the one for managing chronic disease. So my charge to all of you, and I think our conversation for the afternoon, is to think about how do we leverage this still early AI and digitally enabled health age to think about that super convergence of technologies to impact the future of biomedical engineering and beyond. It's not about any one technology. It's not just about AI or genomics, but how we put them together. And it's our opportunity not to just think about where we are in 2025, but to be like Wayne Gretzky and skate to where the puck is in 2035 and reimagine the future of health and biomedical engineering together so we go from now to next in a faster, more impactful way. So let's not take incremental steps, let's take exponential ones. The future is already here, it's just not evenly distributed. It's your opportunity across the entire BMES world and beyond to not predict that future, but build it boldly together. So with that, thanks for the short intro talk, and we'll move to our panel. All right, I'm going to bring all our panelists up, and we're going to start with Mike, who is a real biomedical engineer, and then hear from the others, and then we'll have an interactive discussion, and then open up to the audience. So think of smart questions going forward, and hopefully you can bring up Mike's slide. Well, why don't you, you'll start, and we'll sit here and look smart. You can stand or sit however you like, and we'll go from there. So while we switch over, AI is easy, AV is hard. So hopefully this is going to work.
Let's see, how does this work?
I'm going to pull up your PowerPoint deck off of the laptop in the back, hopefully when they hit
Good morning, everyone. I have 5 slides. And so my name is Michael King from Rice University. I guess I represent the higher education side as well as the publishing perspective. So at Rice University, I teach a couple of courses that are related to prompt engineering and generative AI tools. It's a pretty exciting topic for us. And the classroom is sort of our laboratory. So the students and I explore different concepts and different behaviors of these tools. In this depicted here is, we tested how effective AI detectors are. because they're so important. Originally they seemed like a great solution to detecting the use of AI in homeworks and reports and other things in education. So what's interesting is that if you ask ChatGPT to write you text, feed that into one of the commercial AI detectors like GPT-0 or Scribber, it'll tell you that a percentage of the text is likely written by AI. Now, if you do that again, you prompt ChatGPT to write generate text on any certain topic, but to try to make it human, and rather than AI written, feed it through the AI detector, you will get a very similar result. It doesn't really work. There's out there, as you might imagine or would have guessed, in the AI arms race in terms of detection, there are tools out there that purport to humanize your AI-generated text, like humanize.ai is one of them. If you generate text with ChatGPT and run it through a humanizer and then an AI detector, you get pretty much the same result. It'll tell you that a percentage of that text was generated by AI. All right. So one of my students found a very curious solution that the way to so-called beat an AI detector is to feed, say, Google Gemini with a sample of your own writing. And then if you prompt Gemini to, here's my sample writing, can you generate text on a topic in my style, in my writing? Guess what? The result will pass an AI detector and be reported as 100% human, which really kind of surprised us and shocked us. My point here is that there is no such thing as AI detection when it comes to generation of text. They're not very accurate, they're not reliable, and so they've been completely abandoned and banned in higher education because of the implications of false positives or false negatives. And I think most of us would agree that accusing an innocent student of using AI on their assignment is somehow worse than letting a student get away with it. So at Rice University, we have kind of a unique system. The Honor Council, the Rice Honor Council that handles all academic honesty cases, is completely student-run. It's quite remarkable. They take great pride in it, in the whole concept of the honor code and so on. And before this current semester, back at the end of the summer, the Rice Honor Council sent all of us Rice faculty a set of recommendations on how to mitigate and combat unauthorized AI use. And it's a very reasonable 2-page document with some very clever suggestions, very useful suggestions. They're here, I won't read them all to you, but to summarize, the majority of the recommendations generated by the students is attempting, I think, to remove the temptation of using AI to do work, as well as the opportunity for it. And so I think that, and it's a very reasonable, and it has basically been adopted by most instructors. I think long term, and we'll hopefully get to talk about this, I think long term, as engineers, we need to sort of do the opposite. We need to run towards the fire and not away from it. I think we need, ultimately, I believe that we will be integrating large language models into the entire curriculum. It's really the best because it's out there in the real world. These tools are being readily used and adopted, and we want to give our students those same advantages. Vibe coding, it's surprising to me. I looked it up. This term, which is ubiquitous now, at first it sounded like a joke. It would get chuckles whenever I'd use that term. Not anymore. It was just coined earlier this year. Can you believe that? But vibe coding is really just like it sounds or implies. It's writing functional programs in a variety of languages, just using natural language. And the interesting thing is you don't even need to know how to code to vibe code. And it can write in all these languages. I mean, a couple of those languages I never even heard of before I started reading the articles testing like ChatGPT's ability to program. It can write in any kind of script you can think of. If you think about the training corpus of these tools, they have access to pretty much everything that we've put on the internet, like Discord servers and GitHub, et cetera, Reddit, and so on. And it's quite effective. These LLMs can now translate code from one language to another seamlessly with minimal errors. And here's the really surprising or worrisome thing is that you can also vibe code your way through complex engineering calculations. I'm talking about what's depicted here. This is actually an example from environmental engineering with water permeating through a semi-permeable soil with some boundaries and so on. And what these authors did is with a few different challenging problems, that are like continuum level physics-based modeling, is ask ChatGPT to write MATLAB programs that would solve for this physical problem using finite difference. All right, that's something a lot of us engineers are familiar with and are comfortable with, and we either teach or learn these topics. The caveat is, at least with GPT-4, say last year, the caveat is it really only works if the user is an experienced engineer who has built up the physical intuition to look at a solution and immediately recognize, well, this isn't quite right. So clearly, ChatGPT got one or more of the boundary conditions wrong. Let me iterate by altering my prompt. And so as you can see in that picture, it took 2 additional iterations until ChatGPT was able to solve the correct pressure field, if you will, that is identical to a benchmark solution by a proprietary engineering software that probably costs thousands of dollars. So this is, I think, the future of engineering. The good news for us is that in that we won't be put out of a job is that you do need that expertise, all right? That domain expertise, that's not gonna go away, I don't think. Now, some of you know me from being the editor-in-chief of Cellular Molecular Bioengineering, a BMES journal, for 11 and a half years. And some of you also know me as being an early adopter and sort of like heavy user and fan of ChatGPT and related tools. So it came out November 30th, 2022, if you recall. And by January 2nd, I had published a couple editorials. This one I had sort of the audacity to include ChatGPT as a co-author with me, and for various reasons, this paper's gotten a lot of attention. By the end of January 2023, the editor-in-chief of Science magazine came out with a very kind of dismissive editorial. Didn't really recognize in that article the value of these tools for doing science, but really it was just the point of it was that they will not accept submissions using AI, and even kind of suggested that to use AI to write articles is somehow a form of misconduct or something. I think as the weeks rolled on, the majority of us kind of took a more sort of permissive stance. This is on the upper right is an editorial I published in CMBE in April of 2023, saying that we welcome generative AI in the use of preparing scientific articles. We just want you to disclose its use, clearly cover letter in the article, et cetera. And this was in line and consistent with the majority of the Springer Nature portfolio. Okay, so interestingly, by the end of 2023, more and more journals were going further, saying, we don't just tolerate AI as a writing tool and as a research tool. We encourage it. And you'll notice there, that's New England Journal of Medicine, arguably the most respected journal in biomedicine. And it's their AI spinoff, but they welcomed it. That was by the end of 2023. Just a couple weeks ago, though, I saw a new editorial which really kind of took my breath away because it went further than I thought the field was really comfortable doing. And this was by the editor-in-chief of the Journal of the American College of Cardiology. That's not just one journal, it's a family of journals. And they went the furthest that I've seen, which is that, it starts with an anecdote. A colleague, fellow editor was like, this is written too well. It must have been done by AI. And it got this editor thinking, like, what are we doing here? Why are we like handicapping our actual scientific products with these artificial barriers? And so they made the very bold decision to say, we welcome the use of generative AI in papers, and furthermore, you don't even have to disclose its use. All you have to do, according to this journal, and perhaps others will follow suit, all you have to do is stand by the content. Right? You take responsibility for the content of what's in the paper, and then everything else is really irrelevant. And that's, of course, what we should have been doing and have been doing as authors all along. But it's just really remarkable how this has changed. And I will, before I flip to my last slide, I'll point out that in the medical field, Okay, we all can pat ourselves on the back a little bit, but in the medical field, we've been way out front of a lot of other disciplines in accepting and embracing these tools. And of course, if you saw in the last talk by Daniel, that is true in many, many dimensions other than publishing. So I'm now encouraging all my fellow biomedical engineers to what you think about LLMs, the snap judgments, the casual observers or casual users. You want to revisit them because you might not be up to date on things. Remember hallucinations? This is a big deal, especially when ChatGPT came out. They've gotten a lot better. So if you use GPT-5 and you ask for references, the references now are for the vast majority real. They're not made up like in the past. Facts, scientific facts are hallucinated a lot less with the current generation of tools. And there's so many ways that LLMs can benefit the scientific enterprise. It's extremely good at extracting information from PDFs and other forms of information with great accuracy and great volume. We can summarize papers. We can find new connections between elements in papers, outlining things. So and this is kind of the coolest area. It almost seems like science fiction. I published a couple things exploring, can we just take humans completely out of the scientific method? Can machines form novel hypotheses and go and test them and draw conclusions, et cetera? And in some limited examples they can. But here's a couple of papers that I presented in my class. In one, some researchers, they trained their version of large language model on all of the 2023 abstracts in the Association of Computational Linguistics, a big LLM field. And they trained them on all the 2023 abstracts. And then that LLM was able to correctly predict 77% of the next year's abstracts. Okay, so people like to say, well, AI can't really generate new ideas; it just recombines existing ideas. Well, that's kind of what humans do anyway. And to that degree, this machine was able to predict the next year's scientific program, which is pretty fascinating. There's been other studies looking at the ability of LLMs in generating novel research ideas based on literature, databases, et cetera. And I hate to break the bad news to you, but the LLMs were generating statistically significant greater novelty and excitement in the abstracts. The one where humans still slightly outperformed LLMs in idea generation is in feasibility, all right? But not to a point that it impacts the overall score. And these are human reviewers that look at proposals and judge time and time again the AI-generated proposal to be more impactful and more novel. It's kind of interesting to me, the process that humans, even in a unfettered brainstorming mode, are kind of self-filtering and maybe not expressing novel ideas that we have the problem of having to actually do the research afterwards. So I think that's really a fascinating new development, and we've just sort of scratched the surface. And I'll talk in the discussion, if we have time, about how it's kind of a shame that the NIH has really put up a total ban on the use of AI in proposals. And the data indicates that we could be handicapping our own science with such a restrictive policy. And I think that's it for me. Thank you.
Great.
Good afternoon, good morning, everyone. Just waiting for, perfect. Okay, so my name is Pantea Kodami, and I wanted to put a visual for you to learn more about my background and how it ties into biomedical engineering. So my educational background is in engineering. I did a material science and engineering with focus on biomaterials at MIT for undergrad and grad school. And also I did a minor at the Sloan School of Management because I was always interested in not only developing the technologies, but also being able to bring them to the market and have a real impact. After finishing my education, I started my career at Illumina in San Diego, where I spent over 11 years working on a variety of technologies to enable precision medicine. So I led the launch of 33 different products within the genomics market, and notably the $1,000 genome that was launched in 2013, that at that point was such a fundamental shift in how we look at genomics and accessibility, and obviously now we're at 80 and hopefully less. And after Illumina, I moved to AWS, where I focus on cloud computing and really leveraging the capabilities of the cloud to go from data to insight. I'm also on the board of 2 organizations that are very much focused on STEM education. One is Athena, which is really focused on empowering women in STEM careers. And the other one is ST², which is focused on ensuring that all students, regardless of background, have opportunities and right mentorship for engineering. So my agenda for today is pretty simple. I'll quickly outline my experience across 3 different pillars. And then for each pillar, devices, nanoparticles, and genomics, we'll focus on 2 things. First, what are the current limitations, or what has been the limitations for those technologies? And then the AI revolution, how we're seeing the AI really move these industries and these technologies forward. And finally, I'll look at the convergence of these pillars to form a truly personalized medicine bioframework. And then we'll have some key takeaways in Q&A. So my background is intentionally broad, and it's driven by my belief that the biggest breakthroughs, they happen at the intersection of disciplines. So pillar 1 was devices, where I focused undergrad on designing implantable medical devices, such as knee implants, hip implants, and dental implants. And with devices, we look at a lot of different factors, such as sensing, longevity, biocompatibility, and more. The second pillar was the work that I did in grad school on designing nanoparticles for HIV vaccine delivery. So it's really focusing on targeted drug delivery and using the right materials that can perform the right characteristics in the body. And the third pillar was around genomics. And now that I'm on the data side, it's really around managing this massive scale of genomics and data in the cloud. And the unifying thesis here is pretty clear. These are 3 fields: devices, nanotech, and genomics, but they're all fundamentally limited by the complexity and design iterations. And AI is really the tool that's going to help us across these 3 disciplines. So let's start with pillar 1. And I know in the first presentation, we went over a lot of really great examples of how we're seeing devices really become more adaptable and smarter. But if you think about it from where we have started, most of the implantable devices, while they've been very life-saving, they suffer from 3 critical engineering limitations. First one is around static therapeutic profile. So we want to treat a dynamic living system, a human, with some fixed preset parameters. We can think about pacemaker or several other examples that of implantable medical devices that can respond to some biological changes, but they cannot really incorporate all the different physiological metabolic changes that happens in a human on a second-to-second basis and then react in real time. The second is around the battery hurdle. So this is really around most of the devices that we have implanted today, they require battery replacement, and this comes with the risk and also cost to the patient. And the third one is around the risk of basically biological reaction in vivo. So over time, the body can treat the devices as foreign objects, and it can degrade the surface and function, so resulting in lack of basically implant doing what it was intended to do. The shift that we're seeing with AI is across those 3 critical fields. So first one is around the closed loop system. So the AI would analyze massive amounts of data and continuous these biosignals from the body, not just the heart rate, but also the channel markers and more, and use the data to autonomously tune the therapy in real time. This means precise and adaptive treatment. We're also seeing intelligent power management. And what that means is that ML models that can predict the usage spike and quiet periods and dynamically adjust components to maximize efficiency and then help with extending the battery life. And the third one is around predictive diagnostics. So detecting minute changes in the device function or local tissue response that can allow clinicians to intervene before the device fails or rejection occurs. So moving on to the second pillar is the nanoscale and nanotechnology for drug delivery. So designing the perfect drug carrier is an overwhelming engineering challenge. We face a problem of exponential variables. And the ideal nanoparticle involves optimizing parameters such as surface charge, size, ligand density, and core chemistry. And the number of possible combinations is truly staggering. So it's a design space that is too vast for traditional trial and error. This leads directly to trial and error bottleneck. Every lab test is slow and expensive, meaning we only explore a fraction of possibilities. And the practical result is low success rate. And we're seeing this across pharma, where it takes 10 years to bring a drug to the market and costs billions and billions. So how AI is really helping in this part is reducing that physical trial and error and moving that into in silico design. So today we have several examples of generative chemistry that we're using advanced algorithms to suggest novel molecule structures or compositions that have the highest predicted success rate. We design these molecules on the computer, and we test them on the computers before actually moving them to real lab, which can save us a lot of time and also cost. We can use ML models for high throughput analysis, rapidly filtering and identifying the optimal leads from complex screening data faster than any human can. And also, AI allows for safety prediction, so modeling toxicity and degradation pathways early in the process, which significantly would de-risk the entire development pipeline and save billions of dollars before we actually move to clinical trials. And the third pillar, which is my favorite, is around genomics. So here, really, the bottleneck is around scale. And we're facing a data tsunami. The next generation sequencing instruments, they're generating terabytes of raw data per experiment, and it's rapidly overwhelming both the compute and storage resources that are locally available. And this leads to analysis bottleneck. So even though the cost of sequencing a genome from a core consumable and instrument standpoint has dropped to $80, still analysis is a big bottleneck, and interpreting rare genetic variations or subtle disease signatures from massive noisy data sets is computationally immense and also slow. So the high cost barrier of compute power for complex analysis pipeline, it currently limits our ability to run true population scale studies that needed for discovery across the globe. We obviously have some successful examples across the UK and some populations, but really for this technology to be able to be accessible worldwide, we need a lot of help when it comes to data and processing. So a cloud-based AI is decoding the genome with the speed and efficiency that was never possible. We're using deep learning models for variant calling, which dramatically increases both the accuracy of identifying tiny clinically relevant genetic changes and also reducing false positives and false negatives. Also, with scalable cloud ML, machine learning, it leverages specialized hardwares like GPUs that would allow us to process the entire population of genomic data in parallel, making large-scale research cost-effective for the first time, I think, in history. Ultimately, this leads to the phenotype prediction. So AI models are really good at correlating complex multigenic patterns with observable disease traits to identify biomarkers that are correlated to disease and also predict patient risk with far greater precision than traditional statistics. So this is, I would say, the core takeaway slide. When we connect these three pillars, AI creates truly a personalized medicine loop. And that's, I think, the most exciting part, that AI is really helping us across these different pillars and industries, but really the end goal, as our first speaker, Dr. Kraft, pointed out, is really to get to healthcare instead of sick care, and for us to be really proactive. So looking at the genomics pillar 3, it provides the input. So the patient's unique AI analyzed biological data, their genomic information, their metabolic information, all the proteomic, all the data that is really needed to understand the patient at the molecular level. Then we move to the nanoparticles and really drug aspect of it, and it can act as a customized tool. So AI designed a perfectly targeted drug delivery agent based on the genetic profile. And then moving on to implants, our pillar 1, it provides the output and control. So AI-driven devices, they precisely deliver an adjusted therapy in real time, closing the feedback loop. So the result is the final shift away from reactive and generalized treatments to a truly personalized predictive medicine. And to summarize our journey, again, we're moving through adaptive systems across the board, from nanoparticles that respond to local pH changes to implants that adjust therapy based on continuous biosignals, And the cloud and AI are really enabling both the democratization of advanced analysis and also helping bring complex tools to our labs and our clinical practice. And I think the next frontier for all of us is really this data integration and bringing together different data modalities to make sense of the data, and standardizing the formats and having the right protocols for governance and access to data. And to end my talk, I actually gave a TED Talk in San Diego last year around DNA data and decoding health, and really highlighted how right now, thanks to AI and advancements that we have, really is a data problem and a data bottleneck, and that would really help us to get to the next stage. So thank you so much, and I think as we all alluded to, the future is now, so we should all be excited about building the AI-driven bioframework. Thank you.
Brian.
All right, thank you so much, BMES, for inviting me here to speak, and I'll share a few brief remarks. I don't have any slides because I think we want to get right to the conversation. My name is Brian. I am the president and CEO of Coalition for Health AI. I'm a pediatrician by background. I did train on White 9, so you did bring back a little bit of PTSD when you mentioned that, Daniel. So let me share with you a little bit of the story of the Coalition for Health AI, or CHAI, like we like to refer to it. It's more than spiced tea. The story of CHAI starts in the pandemic. In the middle of the pandemic, I had been asked to, actually at the start of the pandemic, I had been asked to help lead data analytics for the White House COVID task force. And so it was in that setting that we had a public-private partnership. You had the public sector, the US government, working very closely alongside many private sector organizations, health systems, technology companies. We were obviously all focused on the pandemic at the time. We quickly appreciated the impact that you were having when you brought together private sector working alongside the US government. We asked, is there something more that we can be doing? We looked at AI. The central question that started us on this journey was, do we have consensus at a technically specific level that would inform what good, responsible AI looks like for a developer, for an engineer, for the deployment community at a health system, a doctor or a nurse, or the governance, the longitudinal management of it? The answer we quickly came is we don't. We have a lot of really good work happening in a lot of different silos. You saw Daniel just give great examples of many of those. But what we don't have is a consensus definition at a technically specific level about what good, responsible AI looks like. And in a consequential sector like healthcare, I think we would agree that that's probably not a good thing. Poll after poll, survey after survey shows that the vast majority of Americans do not trust AI. Depending on which poll you look at, between 50 to 70%. That's a problem. In CHAI, we believe you build trust through transparency and the principles of responsible AI. I'm not going to go into detail too much in them, but once you have a common definition of what good looks like, you can build a suite of services around that. One of the core pillars within CHAI is this concept of quality assurance. Now, many of you that are here in the room or listening online are part of product development companies. You know what an internal QA, QC process looks like. Every company worth their salt has something like that. What we don't have is external entities that can partner with and support the rapid development of these AI tools in complex spaces where you need to have access to high quality data, but you also need to be able to have the kind of trustworthy entities that can evaluate and determine the level of assurance that these models deployed in devices or deployed as software have when actually used on individual people. And so this concept of assurance resource providers is a real central tenet to what we do in CHAI. Now, if you follow the media, there is a lot of spilt ink about this concept of assurance. There's a lot of misunderstanding about what CHAI actually is and what we're doing. And I won't bother citing any of them. I'll leave it to you guys if you want to look us up online. There's a lot of media attention on this. Let me share a few clarifying remarks on this. One, CHAI is not a regulator. That's up to our public officials, both at the federal level and importantly at the state level. We're here in California. Many of you probably are aware of Senate Bill 53 that was just passed into law. It focuses, I think, appropriately on this concept of transparency and building trust with a deeper understanding about how these models actually perform. when deployed and when used locally. That concept is very difficult in the AI space, particularly in generative AI when we think about measuring accuracy. The other important concept about what we do in CHI is that it's all voluntary. We bring together stakeholders from the tech companies to the health systems, building these best practices or these common definitions about what good looks like, and then using the metrics or the testing and evaluation frameworks that you can derive from that to empower these assurance resource providers. Those resource providers are the organizations that are partnering with health systems, the customers from the tech companies looking to develop these tools, to help build a level of confidence before they buy or while they're deploying and monitoring them, to help ensure that these models actually are effective, are safe, are able to accomplish what we want them to accomplish. That's how we build trust, is through that kind of transparency, robust governance, a deeper understanding about how these models actually work and how they actually perform. Now, I'll end with, I don't know how many of you guys read the New York Times. There was a pretty foreboding article out there about, I think it was the prompt that could end the world in AI. And it talked a lot about, I think, one of the biggest concerns that many of us have in the biosecurity, bioterror space. We have these incredibly powerful models that are able to develop molecules that no one has ever conceived of before. There was a recent example from Stanford, just north of here, developing a virus to help combat E. coli. Again, a virus that no one had conceived of before, no human, but an AI model did. How do we think about accelerating innovation, developing cures to diseases that have plagued humanity for centuries, while also protecting us from the kinds of potential molecules that could be pathogens that could wipe out a good portion of humanity? These are some of the equities and challenges that we are trying to develop the kinds of frameworks to chart a path forward for all of us. This is something that in CHI, we started with 8 organizations. We now have over 3,000 organizations. We have 220 plus health systems, a large majority of Americans' healthcare delivery. They're members of CHI. If you're interested in joining that community, developing that framework, take a look at our website. It's chi.org. Happy to share more. Look forward to the conversation, Daniel.
Great. Thank you, Brian. Just to follow up on that point, because we just discussed the positive sides. You can use AI to design a new drug or a bioterrorism weapon. How do you think about, not beyond a New York Times op-ed, educating the rest of the world about how fast this is progressing and its dangers without stimulating folks to say, I might want to try building that and seeing what happens?
Yeah, it's so in the biodesign, molecule design space, I think the considerations, we oftentimes think hallucinations or creativity are a bad thing, right? I think you saw Mike talk about the concerns that we have when we're writing articles, and there's countless articles out there about GPT confabulating and hallucinating citations that don't exist. I think we'd all agree that's a bad thing. In the molecule design space, that kind of creativity and hallucination is a good thing. And so when we think about creating the regulatory frameworks in the molecule design life sciences space, I would assert that we don't want to create frameworks that narrow that kind of creativity. However, when you move from the in silico to the actual peptide construction in a lab, that's where I think we need to be very careful. There are a lot of examples out there where a molecule was designed, we didn't know what its function was, and we actually started building it, and then you realize, oh my goodness, this, the function of this has this unintended consequence that we didn't look at. And so there needs to be robust, rigorous testing in the in silico space before we get to the actual 3-dimensional peptide construction, because that is where the danger really resides. So that would be my kind of how we think about it, is let's incentivize and create the kind of policies that allow innovation to flourish in that in silico space, but let's have robust safeguards, rigorous testing to ensure we understand the function of the molecule in a lab space before we get to actually building these things, in 3 dimensions.
And that takes insight and proactive education. So maybe a question for Mike and for Brian. Thinking about educating the biomedical engineers, the physicians, the pharma folks, the kid in the garage who now can leverage these tools to design a new element. How do we refigure, whether it's undergraduate, graduate, residency, fellowship, continuing medical education in this new AI age? At Stanford, there's not really a course on AI or digital health yet. A medical student starting medical school today in 2025 won't finish residency until 2033, and that's 3 cycles where we've been from ChatGPT 4 to 6 or whatever, 5 we're in. Maybe start with Michael. Like, when you're thinking about the new undergrads who are coming in, how do you bring this into this age, again, without de-skilling them as they need to become convergent on these platforms?
I mean, we need to act quickly. Rice University just announced an AI major. You can major in AI, and there's not too many programs like that so far. I think what we're going to see a time in the near future where every college student is required to take a course in AI. Even if you're in the social sciences, humanities, it's going to be seen as a foundational science to allow you to navigate the world. We're not there yet. A few of the leading programs in BME a few years back incorporated a data science requirement in their programs, but we haven't really seen AI requirements, but I think we will.
And I would add to that, there's a popular saying that you alluded to, that AI will not replace humans, but humans who are not using AI will get replaced by the ones that are. So I think there's a lot of focus on how do we incorporate AI, both in the education and also in the clinic. And there have been a lot of real-time studies done at Cedars-Sinai across the hospitals where they introduce an AI diagnostic platform and they compare how the clinicians would perform with or without it. And I think consistently we've seen that clinician plus AI usually does better than a clinician alone. So I think those results are promising, and also they are more motivating for people to be more open-minded when it comes to AI adoption. And I think going back to what you alluded to when it comes to drug design, a big aspect of it is human in the loop. So understanding how the AI is making the decisions and transparency, because a lot of time, a lot of these agents or AI systems that we use, they have to be very context aware and almost be knowledgeable, let's say, in CRISPR, or really knowledgeable in RNA drug design. And we want to make sure when we're asking them to do their analysis, to understand what the analysis means, how does the comparison needs to be done. So I think a big element of really seeing the results is having that human in the loop and having that guidance.
If I could comment one more thing. On Wednesday night, Keynote, we saw the example where AI could be more accurate than AI combined with clinicians, which I think surprises a lot of people. One thing that we have to teach is better ways for humans to interact with AI. So prompt engineering techniques, for instance, where if you regard an AI tool as sort of a virtual research assistant, then, and you display a healthy degree of skepticism, there's certain prompts where you can encourage that large language model, for instance, to check its own work, make sure that it hasn't made a mistake. And so I think we all could benefit from better ways to, prompt our way into, encouraging the AI tools to check themselves.
Awesome.
A couple thoughts as a clinician. Whenever I speak with residents or med students, I remind people that AI, so set aside agentic AI for a moment. AI is for the most part a tool. And like any tool, we need to train our residents, our medical students, our physicians how to use that tool. You had a bunch of great examples. You had a stethoscope in your pocket, right? As med students, we're trained on how to use those stethoscopes. As a pediatrician, we're trained on how to use a stethoscope for a neonate, which is different than a stethoscope for an adult, which is bigger. And so when we think about how these tools should be used with our patients, the question I remind every clinician is you need to ask yourself a very simple but important question. Is this tool appropriate for the patient I have in front of me? And there's a lot to unpack in that. What kind of data was the model trained on? What was the training methodology? What are its indications? What are its limitations? What is its intended use? How does the model actually perform on patients like the one you have in front of you? These are the kinds of questions that I would hope in an AI course that we would begin to educate our future physicians about. Because again, if you look at AI as a tool, as a stethoscope that you have in your pocket, right? That one that you have, I wasn't trained on. I wouldn't know how to use that. I know how to use a regular stethoscope. How are we training our clinicians in the future how to use these important tools and be able to understand when to pull out the adult stethoscope and when to pull out the neonate stethoscope is going to be really critical. And I think really important, physicians are struggling because they don't know how to navigate that. And so I think that's going to be a space we're going to really need to focus a lot of work on. Both, I think you mentioned continuing medical education, which is important, but also med students and residents.
And to extend that analogy, as physicians or even patients, we're used to opening that very long drug wrapper that tells you the dosing and the timing and side effects. And I think, Chai, you've now developed something a little bit similar. Can you describe that? So, how do you pick from the formulary? How is it trustable? How was it trained?
Yeah, so we have this concept called an AI nutrition label. I'm sure every one of us has been to a grocery store. If you have time, you turn around the cereal box or the can of soup and you see how many carbohydrates, how much fat, how much protein, the different ingredients. That's a nutrition label. We've developed something just like that for the clinician or for the hospital administrator, and importantly for the patient. Right, and so imagine a high-level snapshot of how these AI models are trained, how they perform, their intended use, their indications, their limitations. All of that is going into these model cards, and that is what we're making publicly available in a registry that will be launching next month.
Fantastic. And just to stretch analogy one level layer, it's often about what data sets you train these with. And many of you are familiar with the Framingham trials for, let's say, cardiovascular disease risk management. That's based on a pretty Caucasian European population in Western Massachusetts. There's the All of Us trial funded by the NIH and Eric Topol involved in. That's trying to build a bit of the Framingham on steroids. And is that going to be more required across AI, medical education, and therapeutics to sort of understand where these are coming from and make sure they're aligned with your particular patient in front of you?
I would say absolutely. I think, going back to integration of AI in the clinic, we have to look at the use cases, and there's some use cases like clinical note documentation, summarization that are just easily adopted, and they're more complex use cases that when it comes to making a clinical decision on a patient, making sure the algorithm you're using is actually representative of that genetic background, of that cohort, female, male. There's a lot of complexity that goes. And I think that goes back to transparency, to being able to interact with the AI and asking, almost pressure testing the AI, do you have enough sample in your database that is similar to the patient that I'm dealing with? So that's, I think, a big part. And going back to the previous question about kind of integration and the next wave, I think we have to zoom out and look at the whole ecosystem and look at obviously our healthcare system is the patient, is the provider, and is the payer. So I always kind of think of what would be the diagnostic code for a clinician with an AI making the decision versus the clinician. I think, to really go beyond pilot to production, we really need to solve this kind of AI, not problem, but AI integration across all the pillars. Patients accepting it, patients trusting it, clinicians knowing how to use it, when to use it, for what type of data to use it, but also the payer and the insurance providers to be bought into the system that is actually causing more efficiency or less cost or some sort of economic driver that they're on board. So back to education, I think we don't need education only on the AI, but also on the economical aspect of AI and integration and adoption of it.
It may even be malpractice in a decade not to use the AI making a diagnostic workup. And that comes back to this idea of trustable AI and the data sets involved. You get what you measure, and you can measure readmissions or hemoglobin A1C, but sometimes you have to program these things with certain values. Our friend Zach Kahani has talked a bit about this. Maybe, Brian, you can summarize that idea that when you're building an AI system, whether it's design a drug, a device, a patch, an EMR plug-in, what values are you going to plug in? Are you going to value economics? Are you going to value patient outcomes? Are you going to value lifestyle of the physician? Any thoughts on that?
So if you ask me, what is one of the biggest existential things that concerns me the most? Certainly biosecurity, bioterror is one, but the other is the alignment problem. And this is a concept in AI engineering that many of you probably are familiar with, which is how do we align these models that we're building that are increasingly more capable, the incredible amount of use cases that you showed in your slides, to align to the values that we have as individuals. And particularly when we think about agentic AI and the use of an AI model that can operate, as a semi-autonomous physician or as a patient advocate, helping you navigate not just your meetings and dialing in and speaking, but potentially helping to make real consequential decisions on your behalf. How do we know that those models know what my values are? And so Zach has a project, the Human Values Project. We actually have a project called the Human Flourishing Project within CHI. But they're both looking at what is the framework by which we can tune these models through reinforcement learning with human feedback or some other process that enables them to be able to navigate your values, my values, your values, because all of us are going to have different values. In CHI, we're working with a number of faith-based health systems for which this is obviously front and center. Bioethicists, the Vatican's gotten involved. And so I think it's an exciting space that many folks are very interested in. I'll be honest with you, we don't have the answer on how to do this exactly. You ask any of the big frontier model developers, I won't share names of them, but some of them have literally 12,000 page or 12,000 step checklists of fine tuning to try to ferret out all of the corner cases related to human values to ensure that these models can adjust appropriately. It's a real challenge. We don't have an answer, but it's a critical issue if we want to be able to use these models in increasingly consequential use cases, in increasingly autonomous use cases that agentic AI promises. We need to figure out that human value problem.
Right. I mean, it's getting quite magical, whether you want to put a gorilla to manipulate your slides or beyond. Maybe I'd ask each, starting with Michael, what's most opened up your mind to the art of the possible, and what's overhyped? And so for this audience and those out beyond that, what would be your sort of top-level example of something that's really synthesizing the art of the possible, but what's also being overhyped?
Oh, that's such a good question. Gosh, where do I start with that? I don't think it. I think that there's a dichotomy between the public's perception of AI and professionals using AI. And that's going to continue to drift because on the public side, we have AI slop. We have really basic, customer service chatbots that are incredibly frustrating for people. And of course, we ultimately answer to the public because they are taxpayers and they help drive, the political landscape and investment in AI. So the practitioners, I think, there really is very little level of overhype. I mean, I think that just the potential for incorporating AI in pretty much all aspects of biomedical engineering is real. So I think it's very exciting times. I think the alignment issue is much broader than medicine. I recently read the provocative book, If Anyone Builds It, Everyone Dies.
Yeah.
And it's really gives you a lot to think about. And so I think we're going to be, even on a more societal scale, we need to really wrestle with true regulation and safeguards that we have not addressed yet.
I think the field I'm most excited about is around drug discovery, and obviously pharma, the cost has just doubled and tripled over time, and the time to market has also increased. So I think being able to reduce a lot of that trial and error and be able to do better in silico design, and we have obviously a lot of great models provided by a lot of different providers that can predict binding, that can predict, solubility, toxicity. So that's an area that I'm personally really excited about. But I think on the hype side, or the area that I'm not excited about, is the fear that comes with AI, and I think it's a real fear. But I like to use kind of this analogy of, a really good sushi knife. You can use it to make the best sushi or kill people. And so I think there is a lot of fear with AI, both in terms of job security, in terms of misinformation, in terms of like creating a fake slide with a gorilla moving the sign. So I think we have to, as a society, we have to really be very open-minded about AI and capabilities, but also make sure that we kind of manage that fear that comes with any new innovation.
Two big things that excite me, and one thing that I think is overhyped that I'll mention. On the exciting thing, so AI has an incredible power to meet us where we are at, be it education or in clinical care delivery. So as a primary care physician who grew up in rural communities, I saw every day, both as a child and as a physician, the challenges that patients have scheduling an appointment, driving hundreds of miles, seeing a doctor to manage their chronic diabetes, and rinse, wash, repeat, do that every 2-3 months. The future with AI in primary care, I think, is incredibly exciting. The ability to have agentic models that are part of moving from just a tool to now a member of a care team, to be able to deliver, exceptional primary care that meets the individuals where they're at in their home, just as kind of you were showing. is going to, I think, lead to a level of human flourishing with many of the communities that have access problems. That really excites me. And just like you, I think the drug discovery, that I think is going to revolutionize concepts like personalized medicine that we've always said is just around the corner. I think maybe it really is just around the corner. I have a lot of hope and excitement, and I've seen, from the pandemic moving forward, how these models can develop molecules that no one has ever thought of before that have profound capabilities. On the overhyped thing, throughout human history, the tools that we have developed, humans have chosen to always be in the loop. We have chosen to control the tool. We have chosen to decide how it's used, when it's used. We still have that choice right now, right? We are building these tools. We are choosing how to use them, how to deploy them, where to deploy them. We're seeing, I think, appropriate levels of anxiety from society about, well, maybe that tool's not quite ready to do that yet. I think that is going to continue to be a reality for us in a lot of ways. I don't think physicians are going to be replaced entirely. I do agree that physicians who use AI are going to replace physicians who refuse to use AI. But I think it's going to be, again, physicians, nurses who use AI, and not this complete, we're going to kind of just step back as a human race and say, AI, you take over. I just don't think that's going to happen.
And back to the thing you pointed out about sort of access, whether it's a rural community or elements of the world with very limited access to clinicians or specialists. Now it's already being built, even leapfrogging in the US. I'm on board with Andrew Ng. We're building a platform in India called Jivi.ai. It's basically a doctor in your pocket. It speaks any language, incorporates Ayurvedic medicine. It also can be your nutrition coach. It can do your vitals. So these things are starting to come together fast in some places. The guardrails likely aren't there, or as many that we might have in the US, but it shows the art of the possible. And at the same time, the art of the possible, back to vibe coding, I started trying that the other week. I took one CS class in college. Now I can build the equivalent of my digital.health platform, which costs quite a bit of money in an hour. And so that democratizes the ability to design a new medical product, or potentially maybe not design a drug, but get that forward. So let's shift gears to some of the headwinds. I mean, we're in a challenging political time, economic time. We can argue maybe catalyzed by the pandemic, and even some of our great successes like mRNA vaccines. We have a pushback from anti-science. How do we help educate the population and move politics in a positive direction? And Brian, you've been in the firestorm of this lately. I don't know what you'd like to share that you've learned, and some lessons for those who are playing in this convergent political meets technology space.
I'll keep my comments really brief on this. AI is moving so rapidly that there is a lot of misunderstanding out there, both about its function, its capability, but also about the organizations that are in this space. There's conspiracy theories that we don't need to get into. In CHAI, our approach is bringing as many of the stakeholders together to begin building consensus definitions about the direction we want to move in together, right? This is something that we cannot do with just the politicians in Washington, D.C., or just the private sector in Silicon Valley, or just the health systems, right? We need to bring everyone that has a role to play, that has a voice, including patients, to develop what direction do we want to move in, right? And be transparent about that, and be open to receiving the kinds of criticism and feedback. I mean, I've been on record sharing, great, I understand the concerns that HHS has about CHAI. I want to understand those more deeply. I want to be able to build a better public-private partnership. I think it's, in spite of kind of the rapid pace that we have around us, there are times we need to slow down and make sure we're including everyone's voice and listening to critical feedback when we can to build a better future for all of us.
Yeah, I echo a lot of what was said already, and I think one of the biggest things we could do during this time is things like this conference, where we really highlight the value of AI, and like what you mentioned in your talk, numerous examples of how it's truly driving clinical value, making humans live better, higher quality lives longer, and really helping us, I think, also from a cost saving. We have a diagnostic odyssey when there are a lot of rare diseases that we couldn't understand what was going on, and genomics really helped shed light on that. And now we're in the area of multimodal, multi-omics, personalized medicine, and really kind of showing both the human value, economic value, so that we can hopefully bring more light to that ecosystem. And I think a lot of these, like anti-science or what we're going through, it's for now. And usually kind of science and data wins. So I'm pretty hopeful and optimistic that it's just a temporary phase we're going through.
Yeah, I mean, I'll just elaborate on one aspect that was brought up, which is the sort of consensus. And so being in the academic field, we're not married to any particular platform. So whether we're vibe coding or doing scientific research, whatever, we have the luxury to try them all. Try like 6 different large language models on from different companies, and look at the results and look for consensus among those machines. Look for outlier cases which maybe are not the best. So if you got your blinders on, you're only using one platform, then that's where I think you can kind of go off the rails. So that's, I guess, one sort of minor concern I have with like proprietary platforms, is that they're sort of like gonna basically commit to one machine and one machine only, and to lose that consensus. Because you think about it, just like if a team of advisors is better than a single advisor, no matter how brilliant that person is. So that's, I think, something that I would love to see enter into the private sector as well.
Speaking of advisors, there was a TED Talk a few years ago about the need to have almost an AI representative in Congress. I mean, think about it. There's one PhD in Congress. There's a few quasi-positions in the Senate, but they're not the regulators and the policymakers aren't necessarily able to integrate all this. Neither can any clinician take all this new information, technology, and potential necessary insights to drive the guidance that's going to take us forward. We're just going to go a little over in our closing element. I want you all to put on your futures hat, right? We're only, as you mentioned, barely 3 years into the GPT revolution. Let's go to BMES 2035. Let's skate to where the puck is going to be. What vision would you like to see manifest, and a little bit about how would you get there? What would your future state be in this magical, convergent, exponential age? Let's start with Brian.
Personalized medicine, as I was saying earlier, I think really is around the corner. The multi-omics, I loved your phrase, digitomics. Is that
the digitome? We're exuding
the digitome,
or digital exhaust
of all of the wearables and data that we're all going to have at our fingerprints. I think is a reality that we're going to see start to converge over the next 1 to 2, 3 years. 5 years from now, I would hope that we have the ability to have really meaningful insight from that leads to the kinds of personalized therapeutics and interventions that will address, a chronic disease that might manifest 10 years from then, but if it's, addressed so now, that's going to save a lot of lives. So I'm looking forward to each of us, I'll kind of make this very specific, having almost like a toaster-sized oven device that allows us to have the kinds of personalized therapeutics that address whatever those specific concerns are that the AI models are identifying because of this convergence of data.
100%. Yeah, that's where you have your printed pill in the morning with the Brian for Tuesday.
Exactly.
Which changes day to day. And kind of the necessity, I think we've all touched on this, is to go from big data to insights to actionable insights, almost wisdom, because no one has an average temperature of 98.6 sitting here. Yet as medicine folks, we're trained to treat the average and look at the old 10-year-old double-blinded placebo-controlled trial. We're now in this sort of continuous data and insights age, and folks like AWS are building the engines to make that real.
Yeah, I would say I'm also, based on my background and the work that I do, it's really focused on, I think, patients becoming the CEO of their own health. And with that also kind of democratization, equity of access to that, because let's say next generation sequencing, we don't see same adoption if you look at the map of the percentage of the population that has been sequenced or actually has access to it. It's not equal across the globe. So I'm really hopeful, that we would, with AI and with kind of the technology that we have now, we can have the patient, really truly patient-centric care, where the patients are keeping track of everything that's happening. They're very informed with decision-making, but not just, in US, but also globally and in places where they need it the most. They have the least, working healthcare system, the least access to doctors. So I'm really hoping that we see kind of technology convergence and accessibility for that.
2035 is a long way from now. It's really remarkable to try and extrapolate with the pace they're progressing. I would hope that by then, first of all, wearables and biometrics will be moved from a curiosity to being very widely adopted, maybe even mandatory in some settings. And I would hope that by 2035 we will have fully solved the privacy issue and security, where there's a push button, for instance, opt out for people who don't want all their vital signs on the cloud somewhere and so on. So I think that will always be a recurring theme, but overall, you weigh the good and the bad, that more data seems to be better in many situations, but it will definitely be interesting.
And back to the opt-in or opt-out, I mean, think how our driving has changed in the last 20 years. We used to have paper maps. Now we're data donors. We're sharing our speed and location, which is pretty private. I think there's a way to turn it off. But from that, we build, again, that Google Maps and ways of driving that can inform all of health and biomedicine if we're collaborative. And so, as you mentioned, 2035 is a long way out. There's Moore's Law, which we all touched on a little bit, whether it's with sequencing or AI. But there's also one called Amara's Law, which is that we tend to overestimate what will happen in 2 years, but underestimate what happens in a decade. And so I think we need to keep the art of the possible open to what's possible in a decade and drive to meet the values and the solutions that we all need across the planet to improve health and medicine for all. So with that, I want to thank you for your time and attention, our amazing panel. Let's go create the future together. Thanks.
Thank you.